Hello everyone, welcome to our daily physics problem. Day number 22. Today we are going to look at the hardest problem ever solved yet. This is a problem from the China's Physics Olympiad, 16th Chinese Physics Olympiad, second round. So it's a Newton's law problem. Let's read the problem. In the x-axis, it's vertically upward. The xy plane is an insulated, fixed rigid plane. At point A, which have coordinate x0, where it's a small block with a charge of negative q. The block is connected by a thin rope with one end, and another end, B, passes through a smooth small hole at the coordinate origin, O, through which the small object can be pulled, and now a uniform electric field is applied to the system, perpendicular to x-axis, and the angle with the z-axis is theta. And the coefficient of friction between the small block and the insulating plane be mu equal to tangent theta, and the static friction is the same as kinetic friction. Excluding gravity, the small block is pulled through the thin line to move it. In the traction process, we agree that the B and the thin line is only allowed to move slowly along the z-axis, and not upward along the z-axis. The small block moves very slowly, so at any point it can be approximated as a small mass in a state of force equilibrium, force balance. If the moving trajectory of a small object is known as to be a quadratic curve, try to find its trajectory equation. So we need to find its trajectory equation. It's a very hard problem, and it's very difficult to see the relation. I didn't solve the first time. I look up the solution. I understand it pretty hardly. So, uh, right above, we want to see two graphs. The left graph is the one you need to solve. The right graph is a hint of the force diagram. So, I want to pause the video, try your own. After you try, this might take a little bit of time. Come back to the video, then I'll show you how I did it. So, welcome back, guys. So, we already have the force diagram, so we are not going to lay out it again. So, let's look at the problem slowly. First, we have a coordinate system, x, y, and z. Center origin O, and there's a external electric field pointing at the z direction, a little bit off, and there's the angle. Because we know the trajectory have to be a quadratic curve, so we know that the the vector of E have to be on the same plane as y and z, because if it's on the same plane of x, there will be no y direction force. It's just horizontal force. So we won't have a quadratic curve equation. So if we lay out E have to be between z and y, we can cut that cross section, we have z and y. Then we know the force acting on the block at y direction have to be negative EQ times sine theta. And the force on the z direction, oops, let's switch that. Oh, I want to switch back. I did it right. So on the z direction will be negative EQ times cosine theta. That's the force acting on the block, different direction. Well, actually, we should make the E on the other side because the electric field accelerates negative charges in the opposite direction. So if we want to have a quadratic curve on the plane, we have to be at another direction. It cannot be here, because if it be here, then the block will be pushed out the plane. So we can put it on the other direction. Then right hand side we solve a system equation that describe horizontal and vertical direction according to x and y direction. Then we know the force balance. We know along the trajectory, the friction force, tension force, and Fy have to be balanced. And F friction have to be tangent to the trajectory. That's a very crucial point. It's tangent to margin. And we define this angle as phi, the angle between the tension force and the x-axis. Then we try to balance the force because we know the block is moving very slowly. So at any moment, it can be applied approximately the small mass is a state of force balance. So we balance the force, we got fy have to equal to t times sine phi plus fy, and t times cosine phi equals to fx. fx and fy are the x direction and y direction of f. Then we know that the Pythagorean theorem, we can solve for f squared. Then we know the expression for xx and fy. We can just use our Pythagorean theorem and our equation identity to solve for x squared by plugging the value of plugging the equivalent equation for fy and fx. Then let's look at the friction. How are we going to express our friction force? Our friction force is the normal force times coefficient of friction. So normal force is the electric field, the force pair of electric field force. Then we know Fz times mu equal to F. Then what is Fz? Fz is negative q times eq times cosine theta. Then the coefficient of friction is tangent theta. So we got F will be equal to negative eq times sine theta, which is exactly equal to Fy, if you remember. Then we plug in Fy equal to F into our original equation. We can now solve for t. So now we got this expression here. Let's cancel out some terms. Fy cancel, sine theta plus cosine theta equal to 1, so we have t squared. And t squared minus 2fyt sine theta equal to 0. Then we divide by both sides by t, we got t equal to 2fy sine theta, sine phi. So that's a very good result for t. Now let's plug t back into our equation. We can find the value of fx and fy. So what is fx? Fx is t times cosine theta phi, so which equal to, we plug in the expression for t, we have 2 times fy times sine phi times sine phi times cosine phi. Then we know fy minus t sine phi equal to fy. Then we plug in our t again, we got fy minus 2fy sine phi times another sine phi, and that will be equal to fy. Then we simplify a little bit, we factor out fy, we have fy times 1 minus 2 sine phi squared. Then we need to remember, because our normal force is tangent, always tangent to our trajectory, so maybe we can use the fact, the tangent is just a derivative. If we know the derivative of a function, we probably can know its trajectory, something about its trajectory. That's brilliant. Let's try to solve it. So we know the expression for fy, we know the expression for fx, we plug them in and try to solve it. Because some trigonometric identity, we know this expression equal to cosine 2 phi, this expression equal to sine 2 phi. Cancel out fy, we got cotangent 2 phi. Oh, and we also need to know that fy is negative because it's the opposite direction of the friction force. Remember, in the diagram, fy is pointing upward and f is pointing downward. But we don't need to don't forget about the negative sign. Actually, it doesn't matter lately, but don't forget the sign. So we got our tangent, we got our derivative, our trajectory from the force, static force. Now let's imagine what is the possible shape of that trajectory. We have, because the rope is getting shorter and shorter, absolutely, we might have a curve like this, a part of an ellipse or circle. And we know that the beginning and the end of the trajectory, the slope at the beginning and end have to be infinity. And there in between somewhere have to be 0. We know the trajectory cannot be this or this, because then you have a long line to go and then stop at y-axis and just going straight down. That doesn't make sense. So the best trajectory have to be a circle or ellipse. Circle or ellipse. And we can identify that by finding the relative maximum of the graph, which is at pi over 4. Ooh, got an interesting solution, equal to pi over 4. So means because it's a right angle, 2 angle are the same, pi and 4, pi and 4 down and above. And ellipse don't have that property because if you have very, very thin ellipse, that two angle won't be the same and they don't add up to 100. Then when they are adding up to 90 degrees. So it have to be a circle. So now we know it's a circle. We just do some geometry, analytic geometry you learn in high school. We have the trajectory have to be equal to x minus x0 divided 2 square plus y square equal to x squared divided by 2 square, which is 4. And that's our final solution.